Okay, let's do the last lesson of the quadratic functions unit. Yay! Okay, example. What this is applications of quadratic functions. So this is basically gasp word problems um, using what we've learned about quadratic functions. Okay, really, most of them are pretty easy. You're just plugging numbers in and understanding what the vertex is and uh, what the x-intercepts mean and all of these things. Okay, so we've got a couple of examples for you. During a high school football game, the height of a punt can be modeled as a quadratic function of time as h of t equals -5 times t minus 1.5 all squared plus 12.25, where t is the number of seconds which have elapsed since the football was punted, and h of t is the height of the football after t seconds. Okay, so we've been using f of x, and that means that some function has been done to x, and the y, and that's the answer. It's basically the y value. So h of t, it's just using different letters because it has meaning in this context. H is height, t is time, and so it just makes more sense that way. Um, and that's all that means. Okay, without technology, determine the following values. The maximum height of the football. Well, you know what? Let's just do a really quick and dirty sketch of this, okay? Because this is a real life graph. Anytime you're starting with time, you're starting with an x value of 0, okay? And time always goes along the x-axis, and h is going to go, or h of t, the height, after time t is going to go on the y-axis. And we know that this is going to be a parabola that opens down. And what else do we know about this? Well, we know that the vertex is at, right here, the vertex is at 1.5, 12.25. So when it asks us what's the maximum height of the football, well, it's 12.25 meters. And how long does it take for the football to reach its maximum height? Well, 1.5 seconds. We just pull that right off of the graph or the equation, okay? And let's write this. This is the vertex. This is the y value of the vertex, and this is the x value of the vertex. Okay, the height of the football above the ground when the punter makes contact with it. All right, here's the thing to ask yourself. How much time has passed when the punter kicks it? Well, that's 0, right? Because that's when the t is the number of seconds since it was punted. So the height of the football is going to be height at time t equals 0. And that means that I can plug this into my equation, and I can go h of 0 is -5 times t, or sorry, 0, because I'm replacing my t with 0, minus 1.5 squared plus 12.25. And if I put that in my calculator, I get 1 meter is the answer. And the height of the football, 0.5 seconds after contact. Well, that's height at time 0.5. So I'm going to replace my x with 0.5. So this is going to be -5 times, not my x, my t. Sorry, my bad. 0.5 minus 1.5 all squared plus 12.25. And my calculator tells me that this is 7.25 meters. Does that make sense? Yeah, it does actually, because it's going to start, it definitely goes up faster earlier, and if this is 1.5 seconds and this is 0.5 seconds, yeah, that makes sense. 7.25 meters, that seems reasonable at least. It's not 30 meters. 30 meters would have a problem, or a negative number of meters, we'd have a problem. Okay. Okay, next step says use technology to graph this equation and verify the answers to A. So let's pop over to Desmos. I've already written it up. Just do this. So let's verify this. And I do want you to sketch this one out because I want you to have a sketch of what we did for the next question that we're going to do. So here's this. My graph goes, it doesn't actually go through 0. My y-intercept here, my y-intercept is at 1, which is what we said, 1 meter. Yep. And our x-intercept, we actually didn't do an x-intercept. We did what's the height of the highest point is 12.25, and it takes 1.5 seconds to get there. And the height at 0.5 seconds. So what I can do is draw a line at x equals 0.5. I did minus again, didn't I? Okay. And where do those lines meet? At 0.5 seconds, it's 7.25 meters in the air. So this is correct over here. Yay. Okay, and our graph is going to look like this, where the vertex is at 1.5, 12.25, and this point right here is 0, 1, and this point here, I need to check this over here, is 3.065. 3.065 and 0. Okay. Determine how many seconds to the nearest tenth the football is 10 meters above the ground. So what we need to do that is we have to use our technology because we don't have the math skills at this point to do this, where I'm going to add another line where y equals 10, and that's going to put a horizontal line there for us. And the ball is above 10 meters from this point here to this point here. So it's from this, if I draw this on here. So this one here is, I'm just going to round it to point, we're doing to the nearest tenth, so I'm just going to 829. And here is 2.171. So I'm going to subtract those, right? It's the difference between them is how long it was above there. So 2.171 minus 0.829, and that equals 1.342, which I'm going to round to 1.3 seconds. That's how long the ball is 10 meters or more, at least 10 meters above the ground. I guess that question is a little bit vague. I should fix that. Okay, the punt is not caught by the opposing team and the football hits the ground. Use technology to determine how many seconds to the nearest hundredth it took for the football to hit the ground. Well, that is when it's at height 0, right? So it hits ground at height equals 0, which happens when t is 3.07 seconds, because we'd round that up. Okay. You will not be asked to calculate that without having access to technology, because that mathematics is beyond the scope of this course. All right. Oh no, sorry, there is one more example. Sorry, I added an example, so this assignment thing needs to go. All right, this is example 2. Terry needs to build a fence to keep the deer out of his garden. He has 60 meters of fencing and will use the side of his house for one side of the rectangular enclosure. So that means that he's making, here's the side of his house, and he's going to do a rectangular garden fence of some sort, okay? And if we call this X and we call this Y, then this side is also X, right? Because it's going to be the same side. It's a rectangle. It's all right angles and everything, okay? But we have to, whenever we're doing this, we only want one variable. So we need to rewrite Y in terms of X. And what we know is that x plus y is the total length of the fence, right? And that equals 60. So we get 2x plus y equals 60. I can subtract 2x on this side and subtract 2x on this side, and I get y equals 60 minus 2x. So the length of this side is going to be 60 minus 2x. Okay, that makes sense. If I add up all those three sides, I get 60 meters of fencing. All right. And then if we think about what this fence would look like, or what the shape would look like, we have an x length of one side of the fence, and we have the y, which is 60 minus 2x. And so let's call this is the length, and this is the width, and this is the area. Okay. And I'm going to, let's just make up some numbers. Okay. So if the x is 1 meter, and then we have a meter down here, our width is going to be 58 meters, and our area is going to be 58 square meters. Okay. If x is 2, then our width is going to be, we've used up 2, it's going to be 56, and our area is going to be 112 meters squared. I guess we should put that in meters squared. If x is 3, we've used up 6, so we have 54, and our area is going to be 54 times 3, which is 162 meters squared. Okay, and then we can keep going, right? And the area is going to keep getting bigger to some point, and then it's going to start getting smaller again. Because if x gets down, if x is, what's the biggest it can be? If x is 25, it can be, if x is 25, then we've used up 50 and our y is 10. And this is going to be 250 is our area. If x is 26, we've used up 52. This is going to be 8. Let's keep going. This becomes 29. This is going to be 2. And 2 times 29 is going to be 58 meters squared. Okay. And I mean, you could say x is 30, but then y is 0 and the area is 0. Okay, and actually that's true up here. If my x is 0, my y is 60, but my total area is 0. Okay, so what we want to do is figure out what is the largest enclosure that he can build. So that's going to be in the middle here somewhere. And how big, so when it asks for dimensions, that means length and width. And how big will it be? That's asking for the area. Okay, and the equation that we're going to use in this, and this question will be on your quiz, this question will be on your test, okay, or one very much like it. Not this exact question, obviously, but something very much like it. So the way we do this is we want to maximize the area. So that's going to be what we're solving for. And the area of a rectangle is length times width. And in this case, the area, the length is x, and the y is 60 minus 2x. Okay, so that's the equation that we're starting with. Now, we can't do anything with the equation written like that. We want to expand this out. So this is a equals 60x minus 2x squared. And then we're going to write it in the way we usually see it, which is minus 2x squared plus 60x. And then you're going to factor it, because we want to get it into, well, we need it to have a useful equation for us. We need it either in vertex form or in factored form. And there is a way to get to vertex form from this, but it's not part of this course. The math is involved, and so it's not part of this course. But we can change this into factored form, because we can write this as negative 2 times x squared minus 30x. Okay. Okay, so this is negative 2 times x minus 30. And we know from this shape of the equation that our y-intercept is a times m times n, which is negative 2 times 0 times 30, which is 0. And our x-intercepts are 0 and 30. And we actually, if we come over here and we graph this over here, like this, what we would graph, we don't actually graph the w, we do the x and the area. And we end up with a parabola that goes like this, where it starts at 0, 0, and it ends at 30, 0 over here. And there's a vertex in the middle. Which is important because the vertex is in the middle, right? So from this, we know that the vertex is going to be 15 something, right? Because it's going to be in the middle between the two x-intercepts. So then what we do is we take this equation over here and we go y equals negative 2 times 15 times 15 minus 30. We plug our x value of 15 into that, and we get y equals negative 30 times negative 15, which equals 450. So that's the maximum area that we can get with this size fence. Okay. And then we're asked to find, so we go back up to the question, we're asked for the dimensions. So if the length equals x, the width equals 60 minus 2x, remember? That was our width up here. So 60 minus 2 times 15 is 30. 60 minus 30 is 30. So the size is 15 meters by 30 meters, and the area is 450 meters squared. And if you multiply 15 times 30, you will get 450 meters squared. Okay. Okay, I know that one was really confusing, but it's an important one. And I just want to make sure, and I'm telling you straight up, it's going to be on the test or the quiz. So just pay attention to how we found things. The other thing I'm going to tell you is that the other way this question gets asked is it's a freestanding shape, so like a freestanding enclosure. So what you have then, let me do this in a different color down at the bottom here. So you have a freestanding enclosure like this, where one side is x, and the other side is going to be, let's say 60 again. This is going to be 60 minus, this is x. So 60 minus 2x divided by 2, okay? Because if this is x and this is x, what's left is 60 minus 2x, but then half of that goes here and half of that goes here. So I can reduce that to being 30 minus x. And that makes sense because if the whole thing is 30 or 60, that was a great line. Let's try that again. If I do this, then this bit here is 30. So this one is going to be 30 minus the x, okay? And then you're going to multiply x times 30 minus x to get your area, okay? I will tell you, so that you can check your answers, that when it's a freestanding enclosure, it always works out to a square, okay? And when it's where this ends up being x and this is also x, and when it's against a building, like it was in our example up here, it's always, whatever this one is, this is always twice as big as it. Okay, so that's what the answer will be, but you have to show the work, okay? You don't have to do the stuff on the right, but all of this stuff that I did actually on the paper, you do need to show all of that, okay? All right, that is it. That is your last lesson for quadratic functions and your last lesson if you're doing this in spring of 2020, last lesson of the course. Okay, have a good day. Bye.